Yeah, I'm not going to be able to see, but if people have questions, Sandra, you'll be able to moderate for me as we go along, because I can only see like 4 people with the way I'm sharing this.
Yeah.
Okay, thank you.
Our speaker today is John Saccoman from Seton Hall University. He will be speaking on extending spectral graph theory results to multigraphs. John is giving this talk in memory of his dissertation advisor, Dr. Charlie Suffel, who recently passed away. John and Charlie wrote 13 papers together, including a book spanning 3 results for graphs and multigraphs. And this was written by John and Dan Gross and Charlie Suffel. He has also written another book, Understanding Sabermetrics, and the second edition is out by Mike Huber and Father Gabe Costa. And the books are right behind him, and you can see that. So thank you, John, for giving the talk today, and the floor is yours.
Thank you, Sandra. Yeah, so we see, control here. Yeah, so this wasn't intended to be a memorial talk for Charlie Suffel, although he did say, I talked to him a few days before the heart attack that he never woke up from. And he did say that he wanted, I said I was giving a few talks, including Boca last week, or virtual Boca last week, and that kind of stuff. And he said he wanted to come, he wanted all the dates and times. So hopefully he's here in some way. But I would not be doing this. I would not be in my profession if it weren't for him. He was a great influence. As you know, you might know, he was the managing editor for the journal Networks for about 30 years, and he was very helpful to other graph theorists starting out, and was very encouraging of them. He helped people in the New York Combinatorics group as well, and graph theory, gave a number of plenary talks at Graph Theory Day, and just always very accommodating in that way. And he'll be missed. In our department, quite a few of us worked with him, or he was our thesis advisor, and it was quite a blow. But anyway, so one of the things we talk about, because the reason I look at spanning trees is because of their relationship to one of the reliability models. In this model, the nodes are perfectly reliable, and the edges operate with equal but independent, very important probabilities. And so in red, you have the all-terminal reliability, where S of I is the number of spanning connected subgraphs of size I. Okay. So for small values of P, the SI term will dominate, and that's your spanning trees essentially. And you want to bound the class, number of nodes and edges, because finding the all-terminal reliability has been proven intractable a long time ago by Ball and Provan. But and this is essentially the old telephone system model, where you had those black telephones that you couldn't break them. You know, they were very indestructible, the old rotary phones. But you had power lines outside, or the phone lines outside. Maybe a tree could fall on it or something. And you know, what is the minimum that you could have that you could still have communication among all the phones? So that was the original model. But I think spanning trees are something interesting to look at anyway as we go forward. So we're doing some preliminary stuff here for later on in the talk. One of those things is the so-called reverse swing surgery. It's reverse swing when you go from left to right. It goes by some other names. We always called it the swing surgery, but it's called compression, I think, nowadays. And there are some other terms for it. They might have called it, I think Colburn might have called it the shift. I'm not sure. But anyway, essentially what you're doing when you go from left to right is you're creating a nested neighborhood between nodes U and V. Their neighborhoods are not completely nested in the graph on the left, and there could be interconnections in the oval. The oval doesn't mean anything in particular. And then when you move those two edges up to the top, now they're incident on V instead of U. Now U's neighborhood is completely contained in that of V. And that's the reverse swing. So if I go from right to left, that's the swing surgery, where you break down that neighborhood nesting. And if UV had been an edge, then it would be present in this surgery as well. It doesn't matter. And I mentioned to Sandra, if people have questions as we go along, you can ask it. Just I might not see you, so somebody will have to let me know. But that's not a problem at all. Another thing we look at is the so-called Laplacian matrix, or as Charlie Suffel and the late Frank Bosch, the late Charlie Suffel and late Frank Bosch called it the nodal admittance matrix if you're an electrical engineer. And so this matrix is essentially the diagonal matrix of degrees of the graph minus the adjacency matrix. And we get a little fancy since we're talking about multigraphs. Instead of a 1, if there's an edge between two nodes, we say m for the number of edges between the nodes. So if there's just one edge, then it's a -1, and so forth. So that's what we're talking about there, the old Laplacian matrix. So Kirchhoff's matrix tree theorem, all the cofactors of the Laplacian matrix are equal, and their common value is the number of spanning trees. What we like to look at is the formula for spanning trees based on this result, and that's simply the product of the eigenvalues. Now I want to talk to you about that eigenvalue product just a little bit. We order the eigenvalues in non-decreasing order from lambda 1 to lambda n. If your graph is connected, then there will be a single eigenvalue of 0, which would be the smallest one. So therefore, as you can see, we start the product at 2, so we're not multiplying by 0. If by chance you have 2 connected components, you'd have 2 zeros. And therefore, the product would be 0 because you have 2 components in the graph, you can't have any spanning tree. 3 connected components, 3 zeros, you get the point. So that's how that goes. So here's an example. This is a K33. I like to include this in my talks because this was the first graph I ever drew on my own in TICS, and Dr. Monica Heinig taught me that. She might be here today. And so that's the graph, of course, the complete bipartite K33, and there's its Laplacian matrix. Okay, so the Laplacian eigenvalues are 0, 4 3s, and a 6. You lop off the 0, take the product of the other guys, divide by 6, and you get 81. So that graph has 81 spanning trees. Now, the matrix that we work with quite a bit, and we're going to work with later, is called Temperley's B matrix. Now, J stands for the matrix of all ones. So if you take a matrix of all ones and add it to your Laplacian, you get Temperley's B matrix. And the only effect on the eigenvalue spectrum is that 1 0 you get for a connected graph becomes an n, the number of nodes. So if you have 2 zeros, only one of them become an n, so it's the same deal. And so you can use this matrix eigenvalues to find the number of spanning trees as well. You take their product and then you divide by n squared, since you don't have that 0 in there anymore, if it's a connected graph. Everybody okay with that? We actually have modified the Temperley B matrix for some of the, we're not doing that in this talk, but say m times j, if m is the multiplicity of edges or whatever, then you can have a matrix of all m's, but then you have to do some other bookkeeping on the thing there. Now, this is the formal definition of majorization. I know that people tend to use different definitions of majorization, but this is the standard definition. You have 2 vectors of really positive integers, x and y, both of which have length n, and whose elements are listed in non-increasing order. Then x is majorized by y, or y majorizes x. If all the partial sums, you always go in the same direction in that inequality, that the sums of the x guys are always less than or equal to the sums of the y guys at each stage. And again, the sums have to be the same. So then at the end, they catch up. So the thing that we like about this result is that if x is majorized by y, then the product of the x's is greater than or equal to the product of the y's. So again, that's a standard majorization. The vectors have to have the same length and have to have the same sum. And if that happens term by term all the way up, then you have majorization. So here's an example. I think Dan did this example. It might even be in the yellow book. So if one vector is 8666, 5522, the other one is 88666, 411, and then you have here, as you can see, the sums as you go along. So you could probably do that mentally anyway. The first term, the first 2, the first 3, always going in the same direction. Y always bigger than x. Then at the end they catch up. And so that would tell you that the product of the x guys is bigger than or equal product of the y's. In other words, 172,800, strictly greater than 55,296. By the way, I saw until my computer, until whatever happened down in Florida blew up. So an excellent talk by Peter Winkler, what I could get of it. And he did say that in any good mathematics talk that you have one joke and one theorem, and prove the one theorem, I should say, one joke and one proof. And I also would say that you also want a conjecture or some open problem as well. And we'll get to those things later. I can't promise on the joke, however. Okay. So another nice result for majorization is if you have a positive definite Hermitian matrix, the vector of its eigenvalues majorizes the vector of eigenvalues. That's a real nice result and something that we like to use. The thing is that our Laplacian matrix and our temporally B matrix certainly fills the bill. Here's an example for the B matrix. So for K33, remember what we said, you replace the eigenvalue of 0 by an eigenvalue of n, which in that case is 6. And so your eigenvalues are 6, 6, and then 4 3s. The diagonals are now all 4s because you added 1 to everybody. And as you can see, the partial sums are always going in the same direction. Eigenvalues bigger than diagonal terms. Like that. You can always make it up in the last term. Okay, so the first result I'm going to talk about is maximizing the number of spanning trees, and I don't think I've presented this for more than 25 years. This was one of the main results of my thesis, or one of the results, not the main, one of the results of my thesis with Suffel, so it was appropriate anyway that I was put it in here. So the graph Kn minus a matching of size k has the greatest number of spanning trees of any simple graph in its class. And that's a node edge class, okay? So n choose 2 for the Kn and then minus the matching of size k. Now, this one happens to have a full matching removed from it. So if you look at the nodes, the top 2 corner ones are missing an edge between them. The bottom 2 corner ones are missing an edge between them. And then the 2 middle ones are missing the edge between them. So that's the matching that we took out. Okay, so it's Kn minus a matching of size k. And Shire proved that in 74, and Kelmans and Chelnikov independently proved it in 74. Now, this was a result from a thesis, and I'm giving credit to Suffel and to Frank Bosch and Danny Gross. Any multigraph in the class of Kn minus a matching having a single multiple edge of multiplicity 2 has fewer spanning trees than Kn minus K2. So, in other words, even if you allow for a single multiple edge of multiplicity 2, Kn minus a matching still beats it for the number of spanning trees. Okay, and again, this was not a lot of people were working in multigraphs, and I guess still not a lot of people. But anyway, so that's a main result there. Now, the way we prove that is we look at Temperley's B matrix, like we talked about. So if I think about the B matrix for the Kn minus a matching, the eigenvalues vector will dominate the degree sequence vector. So the product of the degrees is less equal to the product of the eigenvalues, okay? Now, so if I have, so there's the B matrix where M is some multigraph in the same class, and then there's the B matrix information for the Kn minus a matching. So of course, things are going that way. And they just put the tilde on top of that to indicate that it's a vector of stuff, okay? So let's say that we show that the degree sequence of the B matrix majorizes the eigenvalues of the Kn minus a matching in that class. Then what does that tell you? Well, that the product of the degree sequence guys is less equal product of the eigenvalues. And we already know that this happens. So that goes on the other side over there, and you get this. So you can show that if the product of the eigenvalues is 1 is less equal to product of the eigenvalues of the other, then the larger one's going to have more spanning trees. You know, once you divide out the n squared, you'll have the exact number of spanning trees. Okay. Now, this result holds for a large number of the cases, but there was a small number of exceptions. And I think Dan had written a Pascal program at the time, tells you how long ago this was, to come up with some of the exceptions to this. And the vector of diagonals of a multigraph, or the B matrix of a multigraph, will not majorize the vector of eigenvalues of a Kn minus a matching in the same class if and only if this degree sum happens, that from the n minus k plus 1 to n, the sum of the di's is greater than k times n minus 2, and that's equal to the eigenvalues of k minus the matching from that point on. So when that happens, that will not majorize, and so we had to break that down into when that was going to happen. Okay, so the exceptions were covered by exactly one node incident on that single double edge or single edge of multiplicity 2 is a full neighborhood. Both edges incident on that edge are a full neighborhood, meaning they have this, they know everybody, all the other nodes, and neither node incident on double edge is a full neighborhood. So we broke it down to those cases, and that's how we proved this. If any of you were alive in 1996, this result was presented at the AMS meeting down in Orlando. We had to fly out late because there was a blizzard, and wound up flying out the night before I had to give my first research talk. No pressure. Okay. So now I want to expand some of the stuff that was talking about the spanning trees of multigraphs. So this is the drawing that we're going to use for split graphs. And these are the ones we're talking about now. We're going to talk about threshold graphs, of course, later. But this is a non-threshold split graph. Whenever you see a rectangular box, whenever I draw something in a rectangular box, that indicates a clique. So this is a clique of order 4 here. And these are the nodes incident on it that we always called cones. Now, another thing about this particular split graph is all of the cones have the same degree. They're all of degree 2. So we call it a proper split graph. We use the word proper when all the cones have the same degree in any sort of these graphs. Now, I'm just showing this to show you a little bit of the nomenclature here. So 3 IPS 6.2. The 3 stands for how many nodes outside the clique nodes are incident on. Okay, the 6 tells you how many cone nodes there are, and 2 tells you the degree of all the cones. Okay, so 6 cones, each of degree 2. Now, this guy has a spectrum, 0, 1, 4 2s, a 5, 2 7s, and an 8. In general, that spectrum will look like this, and it has these these roots of a quadratic. Back in 2006, Russell Meris had, well, I think it happened earlier than that, but he had some open problems, and one of them was, do there exist any non-threshold split graphs that have all integer Laplacian eigenvalues? This is an example of one of them that a student at the time, now she's Dr. Jessica Fuller, teaches up in Connecticut. She and I found this and developed an infinite class using essentially matrix methods. At the same time, Kirkland and his group also found that at the same time. When I informed Mary, said, hey, these other guys were working on it too. So it was around 2010, 2011 that this all came out. But anyway, so that's just to give you an idea about split graphs. Oops. So that's when they're Laplacian integral, when that discriminant is perfect square. And you can't just generate these for every number, but 2 IPS 8.2 is not Laplacian integral, and 2 IPS 7.2 doesn't even exist. Those parameters can't be realized as a graph. So has nothing to do with multigraphs, but just thought it'd be nice to mention and give you an idea of the split, get you in the split graph thinking of things. So one multigraph that we've talked about is this IPSM, and we have 3 parameters, but it's probably just as good to say there's 2. Notice the exponent of mu. The mu represents essentially how many edges there are between each pair of nodes in your clique. So this is a multi-clique, if you will, where every node is adjacent to every other node exactly mu times. So they have to have the same degree in this example. Some of the examples we look at later, they get a little more wild. But anyway, so that's what's going on in here. I know it's hard to tell from the picture that you can't tell if it's a multi-clique or not, but you have to know by the name because we put that mu up there as an exponent. And so again, sticking with our naming convention, the first one tells you that each clique node knows exactly one cone outside of the clique. There are 6 cones, each of degree 1. And then that other 0 would be, it's a parameter that we save in case there are other nodes in the clique that aren't adjacent to any cones. They would be there and they would be counted in that third parameter. Everybody good with that? Makes sense? So hard, I can't see anybody. Okay. Okay, so now, so we developed a generalized family of these. You know, you start with a base and then you work up to these pictures. And so you get this whole generalized family of XIPS multigraphs, and we're able to generalize and get a formula for their spectra, their Laplacian spectra. So that was there's another example, the IPSM 1230 to the mu. Can we start building on that? It's almost like you see there are little clusters develops around particular things. So it's almost like they're little split graphs on their own, even though all the clique nodes are adjacent to each other in there. So here's the theorem for this one. Oh, I apologize. Part of the polynomial is truncated. I apologize. So for all of these multigraphs, these are what the eigenvalues would be. And again, the modus operandi here is that once we set up the nomenclature for the split graph, the eigenvalues are very often dependent on those parameters. So that's the parameters in the nomenclature. And so that's how that one works. For the way they have to cluster like this, and a lot of stuff has to be the same. If you notice, all the cones are of the same degree. The clique nodes are going to have their own degree as well, and you'll have the same multiplicity of the in the clique edges. Okay, so now we're going to talk about the threshold graphs a little bit. Now, the threshold graph is a special case of the split graph. I think people know that. It has the nesting of the neighborhoods. And in fact, that's one of the uses for the reverse swing surgery. The reverse swing surgery will reduce the number of spanning trees. When you apply it from one graph to the next, it will reduce the reliability if you do the reverse swing. Also, if you keep applying the reverse swing to some graph, any graph you want to talk about, eventually you will come up with a threshold graph. And the reason we talk about that is because, as again at the beginning, for the ultimate reliability, it's intractable to compute, so you want to at best bound your reliability. And so the threshold graph is the one that's going to provide your best bound. Okay. So again, the definition of a threshold graph: given any pair of nodes in the graph, we have that neighborhood nesting happening whenever. If my degree is smaller than yours, that should be a small u. If my degree is less than yours, then my neighborhood is nested in yours. Okay. Now, besides that neighborhood nesting property, threshold graphs are also uniquely realizable by their degree sequence. In other words, that degree sequence up here, the 7, 8, 8, 10, 10, 10, and so forth, that is only realizable as a threshold graph in the simple graph world. That's one of the things that we've been trying to do, is to try to characterize multi-threshold graphs. And we're going to talk a little bit about that as we go through. So in '96, in discrete math, Hammer and Kelmans came up with a formula for the eigenvalues of a threshold graph. It's a very nice formula, except that it does not work in all cases. And that name is Dr. Sarah Bleiler, who's teaching over in Tennessee now, one of our students. And we noticed the error in the formula and published the correction. So basically, if your threshold graph has an odd number of terms in its degree sequence, then the formula in the Hammer and Kellman's paper holds. If it does not, then you need to use our formula. And again, we found that by happenstance because, you know, first theorem, well, corollary to the first theorem of graph theory, whatever, sum of degrees is twice the number of the edges, right? And even number of odd degree nodes, all that stuff. Well, the sum of the eigenvalues when we applied their formula to an even case came out to be odd. So that was quite sobering and lucky. Anyway, so here's the odd case. Again, there was a degree sequence. And so you get the eigenvalues in that characteristic polynomial very nicely there. I have an extra parentheses, sorry about that. But the whole thing, I think, relies on this K, which is the floor of S minus 1 over 2, where S is the number of unique terms in the degree sequence. And that's essentially breaking up your threshold graph between the cones and the clique nodes. And that's in fact the definition of a split graph, right? You can partition the node set into those in the clique and those in the independent set. And that goes a little kaflooey in the even case, which we'll show you in a second. So this would be the even case. Let's see, do I have the degree sequence? Notice that I've made these guys red, and those are two nodes of degree 10. One's in the clique, one's not. Okay. And again, if you tried to apply the original formula to this, it would not go well. Because there's that ambiguity. Am I putting it in there? Am I leaving it out? And as it turns out, you do this, it's kind of telling you to put it in. So there's the characteristic polynomial factored into its eigenvalues. Okay. Again, this was not multigraphs yet. So let's start talking about multigraphs. Another old result, if you have a complete graph with all edges of multiplicity mu, and then the eigenvalues are 0, and then the rest of them are n times mu. And this we proved to be a unique multigraph that has the greatest number of spanning trees in its node edge class. And essentially, a complete graph is nominally a threshold graph, so we throw that in there. And we actually use that special Temperley's B matrix for this. We just add a matrix of all mu's and add that to the Laplacian matrix. And so this is a result that Dr. Monica Heinig did with me when she was an undergraduate. And we have here our threshold graph, and then we have a second box over here. And what this box is a clique within the clique, that there are multiple edges between or among the nodes in there. And then they know the guys outside there once, and these guys know each other once. Okay, so you have kind of a sub-multi clique, if you will. And the notation would be that there's 7 nodes total. The two cones are of degree 2. And then there's the multiplicity of the multi-clique is 3. And so that's all there. And the way you get that, why you know there's only 2, is because the degree of the cones tells you the order of the multi-clique, the sub-multi-clique within the clique. Everybody follow that? So that's 2. It's 2. If that was 3 to the 2, then there'd be 3 guys there. Okay. So the degree sequence is 884422. This Laplacian spectrum is 022557711. Now, this is one of the things that we were trying to use to come up with a notion of a multi threshold graph. So we have neighborhood nesting, and we have neighborhood nesting in the multi-set sense. So in other words, instead of just saying, okay, if my degree is less than or equal to you, then my neighborhood is contained in you. It's also the number of times I know you as well now. Okay, so that's why we just have the multi edges inside the clique, and those are your dominant nodes. So that's sort of things we're trying. Okay, does this make sense in terms of the definition of the threshold graph? So here's the generalization of that formula. So you have this very special MT, we called it. It could be for multi-threshold. We're not prepared to say that it's threshold just yet. So for S odd, the Laplacian spectrum looks like this. Okay. And the exponents just stand for the multiplicity of those values in the product. So it's just notation there. And we made a special case if it's even, then we have one fewer factor in the product. So that's the formula for the eigenvalues of those particular multi-threshold graphs, always integer. So that's one hopeful thing, because threshold graphs will always, in a simple graph world, threshold graphs will always have integer eigenvalues based on that formula. Very similar, very closely. The spectrum is very closely aligned with the degree sequence. Not true of split graphs in general, though we showed you an integral one, but there really aren't others that we know of. Most split graphs have non-integral spectra, or at least one non-integer spectrum. So that's that one. Okay. Now, another characterization of threshold graphs is that the degree sequence is unique. Unfortunately, that does not hold in the multigraph world. So that degree sequence of the graph, the multigraph we just looked at, let me just go back. That guy over there, 884422, 884422, can also be realized by this disconnected mess of two multipaths like this. So that the uniqueness of the degree sequence doesn't hold the multigraphs. So it was an interesting suggestion. I gave a talk back in Pennsylvania a few years ago, and the great Garth Isaac was there. And he suggested, instead of looking at the neighborhood nesting, what about the uniqueness of the degree sequence realization? But unfortunately, it doesn't work. So now we have another, like I said, things are going to get a little wild. So we have now graphs which are underlying threshold, and they have multiple instances of multi-cliques. Okay, so now the notation is getting a little rough, but again, it's a K7, and then I have two K2s where the inside there, they're multiplicity 3. And then of course, in the clique nodes, know everybody outside their sub-multi-clique once, and these guys know each other once. And then there's the independent set is of order 3 and degree 4. So tells you that there. So again, I like for the notation to be able, you see that notation, if you know the code, you can draw the graph yourself. And so this multi-threshold candidate, again, this does, the multi-set neighborhood nesting is also realized in this graph. And again, it has integer eigenvalues, just like our friend in the simple threshold graph. And that was with student Joe O'Connor, and he's now an actuary. But we're still in good terms. So the generalization of that formula, and that's where the eigenvalues come from. So again, a few parameters, n, c, k, mu. We called it mu1 because we're going to generalize that a little later. But that's the several sub-multi-cliques in there. So again, working towards a threshold graph characterization for multigraphs. Not quite there yet. Another thing that we worked on, and here's the conjecture. This is called layered proper multi-threshold graphs. And now it's like the Wild West. You got an inner clique here, and another one here, and another one out there. So it's getting a little nuts. And I'll have a picture that helped to discern what's going on in there. But again, the guys in these layered multi-cliques only know only single edges to the guys outside it, and these guys outside it just know each other once. So it's just some multiple stuff going on in there. Now this graph has a degree sequence, 3 instances of 4, 2 instances of 5, 1 of 11, 1 of 13, and 2 of 15, and the Laplacian eigenvalues, again, all integers. Because again, we're still honoring that nested neighborhood property in the multi-set sense. 0 and 3 4s, a 6, a 9, 13, a 16, and a 20. When you have simple graphs, the maximum eigenvalue is n. You don't always realize it either. But these multigraphs, things get big. So inside the nested the layered multi-clique. Okay, so these two guys have 5 edges between them. Okay, K2 to the 5th, like that one there, and then this. Now it's a multi-clique on the 3 guys. So these 2 guys know that guy 3 times, K3 super 3. So it's 3 edges there, 3 edges there. So that little triangle, the top triangle like that, is those guys. And then this guy over here is the K4 super 2. So he knows everybody twice. So 2 there, 2 there, and 2 there. So that's our conjecture. We believe that we have a formula for that. I haven't worked on that one in a while. That's what's going on there. Now, another matrix that is sometimes talked about, and more so recently, is the so-called signless Laplacian. Now, the signless Laplacian is different from the Laplacian. It is the diagonal matrix of degrees added to the adjacency matrix, not subtracting, not D minus A, but D plus A. And it's called the Q matrix a lot of times. And so here's for our old friend, the complete bipartite K33, where I had negative ones before and I have positive ones, you see. And same degree sequence down the main diagonal. Signless Laplacian doesn't help us with too much stuff. It doesn't give us spanning trees. It does count the number of semi-edge walks, though, which is, I guess, a good thing. I think I spoke at this seminar a few years ago. I think we talked about the signless Laplacian, if I'm not mistaken. I apologize if you've seen some of this before. Now, we want to talk about ideal proper split multigraphs. So now we want to talk about a split graph that is a split graph that's a multigraph. Now, instead of the multiple edges being inside the clique, their edges outside the clique, like that. Okay, and so there's the mu, that's the multiplicity of the multiple edges. So we're trying to maintain the same notation as before. The X tells you how many guys outside each guy inside knows. So he knows 1, 2 guys outside. Everybody knows 2 guys outside. So that's a 2, where the X is. IPSMC, number of cones is 2. D, the underlying degree of the cones is 3, and then times 2 for the multiplicity of the multiple edge. So that's what we have there. And this is one way to determine realizability. Mu is CD minus X, or dx minus X squared. And that'll give us some. Okay. Now, oh yeah, I should have said that. These graphs, it's a way of getting a regular split graph, by the way. Okay. Guys are regular. Everybody in this graph is of, every node in this graph is of degree 6. Okay. And when you have a regular graph, and this is why so much work was done with the adjacency matrix over like in the 60s and 70s and stuff, is that you can use the eigenvalues of the adjacency matrix of a regular graph to find its spanning trees without having to go into any of the Laplacian stuff. So your first eigenvalue here, your alpha sub 1, that's always going to be R, which is your degree of regularity. So you lop that off, and then it's R minus, or the product of R minus all the other guys divided by N. So when you have a regular graph, you can use that. So here's what the adjacency matrix for our friend over there looks like. Okay, our split multigraph. And we want to apply one other theorem, which is kind of interesting. If you have a regular graph, and if it has adjacency matrix that are all integer eigenvalues, then your Laplacian eigenvalues will also be integers, and your signless Laplacian will be integers. That's because of this result that appeared a lot of places. Let's call these guys, Pekovic, Rowlandson, and Simic, in their book, and that's where they present it. And so you have your alphas are your Alpha i's are your spectra for the adjacency matrix, and then R plus and R minus for the, depending which Laplacian signless or otherwise. And so that was nice to find triply integral graphs, and this these regular ideal proper split multigraphs are like that. So we already found the adjacency matrix eigenvalues for that one. It was 6, -4, 2 instances of -1 and a 0. So when you add when you subtract the 6 or you add the 6, you get these guys. And then the spanning trees, 588. And if you use the Laplacian, you also get 588. So that's a nice bonus. You could use either one. Once you have one, you got all three for the regular ones. And again, not a lot of talk about regular split graphs because very often you can't get that. But you have to, by goosing up the cone degrees with multiple edges, you get bigger. And so this is work done with the 2 undergrads at the time, Liz Newman and Bianca Riley. And we broke it down into families, and much like the Mafia and the Godfather, there were 5 families of these things. And so this is the head of the 5 families, the first one, and different parameters. So X, IPSM, X plus 1X, and the degree of regularity has to be X squared plus X for this part here. And then there was a family with X, then 2X minus 1 times 2, and there's an example from that family. And so we have we're able to prove the spectra for those 2. And then also the third family, which I'll show you in a minute. And then there's 2 other families that they're very small families. Each of them has only 1 entry in them because they don't fit into any of the other 3. So either there's more that we're missing, or we got to redefine these other 3 to fit those 2 in there. There's the third family. X plus 2 times X plus 1 over 2. That's the 5 IPSM 7.3. Again, it's hard to draw those multiple edges, so just take our word for it. Every cone edge is of multiplicity 3 in that one. And so there's the adjacency matrix for family number 3 of that one. Now, just to give you a flavor of what's going on, in general, the way these proofs go, because we're working with undergrads, we break the matrix into quadrants. I guess we were working with the adjacency matrix in this case, working on the quadrants, and then we just try to create an upper triangular matrix through raw operations in a very algorithmic way, and we do that systematically. Make the M3 all zeros, and bottom of the M1 and all that kind of stuff. So now the last topic I was going to talk about today, and this will be expanded upon at the SIAM conference this summer in July, and that's the notion of strongly regular graphs. And so strongly regular graphs are regular graphs that have some other conditions. So obviously, if it's a regular graph, you have to have nodes, and you have to have a degree of regularity. But there are 2 other parameters that make them strongly regular, and that is A, the number of common neighbors for every pair of adjacent nodes, and C, the number of common neighbors for every pair of non-adjacent nodes. And I think K33 is a good example because it's very clearly delineated as who's adjacent and who's not adjacent. So the adjacent nodes, for example, are like take 1 on the top, 1 on the bottom. So the common neighbors for every pair of that's got to be, well, how if they're adjacent to each other, they don't have any common adjacency, right? And then if they're not adjacent to each other, they have all common adjacency. So that's 6303 for that one. Okay. Now, there wasn't much done in the area of regular multigraphs, but an undergrad, Leah Meisner, and I spent a couple of years actually studying this problem and trying to characterize strongly regular multigraphs. And also another nice thing about strongly regular graphs is if a graph is strongly regular, then its complement is strongly regular. And so again, one of the issues in working with multigraphs is there is really no true topological complement to speak of. I mean, you can get a multi-complete graph and then subtract your thing from there or something. We're still working on that. In fact, that's what we had to do in the thesis. We had to create our own artificial topology because there was no topological complement. But anyway, so if your graph is a strongly regular graph, so is its complement. And so the complement to K33 is just two disjoint triangles. It's also strongly regular. Now here's where the spectrum result comes in. It's kind of a definition or an if and only if condition that if you have a K-regular graph with exactly 3 adjacency eigenvalues, then you're strongly regular. If your graph is strongly regular, it's 3 adjacency eigenvalues. And this is the spectrum for that. Again, your degree of regularity of multiplicity 1, and then this quadratic is determined, and this is the multiplicities of the roots there, and that gives you the whole idea. So that's the strongly regular graph. I don't know if people look at that. So what we did is we did what we call a multigraph inflation. So if I have my K33 super 3, what we've done is we've inflated every edge into a triple edge. Okay, and so that's our inflated K33, as you can see. And as you can see in the heading up here, it has exactly 3 distinct adjacency eigenvalues. Your positive 9, your negative 9, and 4 zeros. Okay. So we came up with a theorem that a strongly regular graph that is formed by, well, let's just say a strongly regular graph that you uniformly inflate to a multigraph will also have 3 adjacency eigenvalues. Didn't see that. We looked. We didn't see anybody else had done it. So let the multigraph be the uniform, and this is the proof that Peter Winkler said we should have. So let M be a multigraph that has uniform mu inflation, showing the regular graph G with multi-edge of multiplicity mu, and we have our adjacency matrix. Then this would be the characteristic polynomial for the multigraph. Okay. So here's some of the gory details. I could factor a mu out of each row, and so that becomes mu to the n times the determinant of that guy. And here's our kind of factoring that stuff out. But what happens? I'll let alpha 1 be beta 1 over mu, and alpha 2 be beta 2 over mu, and alpha 3 be beta 3 over mu. And after we substitute in, we get 3 eigenvalues. So every uniform mu inflation of a strongly regular graph G has exactly 3 distinct eigenvalues, leading towards possibly the characterization of strongly regular multigraphs. We've done in this way. And so there'll be more about this this summer. But in any case, that's where we are. And here's some of our friends at the 75th birthday conference for Charlie Suffel. We hope to hold a memorial conference celebrating his 80th birthday next spring at Seton Hall. Thank you.
Let's thank the speaker.
Thank you.
Questions? So if no one has a question, maybe I can ask one. I wanted to go back to
Go back to what?